Hello everyone, welcome to the channel Learn Math with Shobita. Welcome to another episode of the learning. Today in this video I am discussing some questions from real analysis. First question, which of the following spaces is not complete? Option A, the open interval 0, 1. Option B, r to the power n. Option C, the singleton set 0 union set of all 1 by n such that when n belongs to n. Option D, C of r, that is set of all continuous functions on the real line. Okay, so we have to check which one is not complete. Okay, what do you mean by a complete metric space? Let us see. A metric space in which every Cauchy sequence converges is said to be complete. Okay, so let us see in which space the Cauchy sequence converges. We have the following theorem related to Cauchy sequence. First point, in any metric space X, every convergent sequence is a Cauchy sequence. If X is a compact metric space and if sequence Pn is a Cauchy sequence in X, then sequence Pn converges to some point of X. Okay, so in a compact metric space, every Cauchy sequence converges. So every compact metric space is complete. So here the option C, singleton set 0 union set of all 1 by n such that n belongs to n is compact because it is both closed and bounded. This one I have explained in the last video. Okay, so this one is a compact. Since it is compact, every Cauchy sequence in a compact set converges, therefore it is complete. Okay. Next, in Rk, every Cauchy sequence converges. Okay. So Rk is also complete. So here option B, R power n is also complete. Thus, that is I have explained this. Thus by above theorem, all compact metric space and all Euclidean spaces are complete. Okay, now also another point, every closed subset E of a complete metric space X is complete. Now an example of this one is an additional information. An example of a metric space which is not complete is the space of all rational numbers with d of xy is equal to modulus of x minus y. Okay, so the set of all rational numbers with the usual metric, the absolute value metric is not complete. Okay, so next we have to check the options, option A and option D. Already we got option B and option Z are complete. Now let us check option 0, 1. Let us check the option interval 0, open interval 0, 1. The open interval 0, 1 is not complete because the sequence 1 by n is a Cauchy sequence which is converges to 0, but 0 is not a point in the open interval 0, 1. Therefore, a Cauchy sequence 1 by in the open interval 0, 1 is not converges. Therefore, it is not complete. So only option is option A. Okay. Next, that is option A is the correct one. It is not complete. Now, what about continuous function on R? Let us see. C of R. C of R is complete under uniform convergence norm. Okay. So, I will not prove this. What is C of R? This is space of continuous functions on the real numbers. It is complete. Here, option A is not complete. Next question, which of the following is not correct? Okay, here they have given statements about countable and uncountable. So let us see which one is not correct. Set Z of all integers is countable. So this is true, we know already. Set of all rational numbers in the closed interval 0, 1 is countable. This is also true. Why? Set of all rational numbers is countable and set of all rational numbers in the closed interval 0, 1 being a subset of countable set is countable. We have subset of a countable set is countable. So here the set of all rational numbers is the in the interval closed interval 0, 1 is subset of set of rational numbers. Therefore it is countable. Now The Cantor set C is countable. So option C, the Cantor set C is countable. This option is not correct because the Cantor set C is uncountable. This is one of the result. Okay. They have asked to check which one is not correct. So option C is not correct here. We have to tick option C. Okay. Next, the set of all n comma 1 by n square such that n belongs to n is countable, where n is the set of natural numbers. Whether it is correct? Yes, it is, because we have choosing the first ordinate from the set of natural numbers. We know that set of natural numbers is countable. Therefore, this is also countable. We can make a bijection map from this set to set of all natural numbers. Okay. So option D is also correct. Here they have asked to which one is not correct. So option C is not correct. Next question. Let A be a connected subset in the Euclidean space Rn, n greater than or equal to 1, having at least 2 elements. Then number of elements in A is. Okay. Given A is a connected subset of Rn having 2 elements. Okay. At least 2 elements. Then we have to check the number of elements in A. Okay. For n equal to 1, the Euclidean space will be R, real number. Okay. Here A has at least 2 elements and therefore A is a non-empty connected subset of R. We know that a non-empty subset X of R is connected if and only if X is an interval or singleton set. This result already I have told in one of the previous video. So here A is not singleton, therefore since A contains 2 elements, A is not a singleton set, therefore A must be an interval. Since A is an interval, the number of elements in A is uncountable. So option C, uncountable, is correct one. Next one, let an equal to 1 plus minus 1 to the power n by n whole to the power n. Then limit supremum of an and limit infimum of an. Okay. When n is odd, then an is equal to 1 minus 1 by n to the power n and limit n tending to infinity is 1 by e. If n is even, then an will be 1 plus 1 by n to the power n and limit n tending to infinity of an will be equal to e. Therefore, limit supremum of an is equal to e and limit infimum of an is equal to 1 by e. Option A is the correct one. If sequence an is a sequence of positive real numbers such that an plus 1 is less than r into an for some r belongs to 0, 1 and for all n belongs to n, then which of the following is true? We have to check whether the sequence is divergent or convergent. If it is convergent and converges to which value, we have to check. Given an plus 1 is less than r into an. Also r belongs to 0, 1. That is r0 less than r less than 1. Okay. Now this implies an plus 1 by an is less than r. Now limit n tending to infinity an plus 1 by an which is less than r which is less than 1. So since limit n tending to infinity of an plus 1 by an less than 1, limit n tends to infinity n equal to 0. This is one of the result. Okay. If limit n tending to infinity of an plus 1 by an is less than 1, then limit n tending to infinity of an equal to 0. If limit n tending to infinity of an plus 1 by an greater than 1, then limit n tending to infinity of an will be infinity. This is another result. So therefore sequence an converges to 0. So option B is correct here. Sequence an converges to 0. Okay. Now let us check. So converges to 0. So an is divergent is false. Also an converges to non-zero real number. This is also false. Now let us check whether it is strictly increasing or decreasing. Since r is less than 1, r into an is less than an. Okay. So that an plus 1 is less than an for all n. Therefore, sequence an is strictly decreasing. This is why they have given an plus 1 is less than r into an and this r into an is less than an because r is less than 1. Okay. So therefore an is a strictly decreasing sequence. So an is strictly increasing sequence. This option is also wrong. Okay. Next question. The segment AB of the x-axis in R square, whether it is open or closed, we have to check. This is an open interval, and we know that open interval is an open set. Therefore, the segment AB is open. Thank you friends. Please share and subscribe the channel. If you like, please like the video. If you like, please share the video.